Hi, this is Aaron Jerome with Jerome Electronics. Today I would like to talk about transistors. Now, this is a newer subject to me. I haven't been into this as much as, or as deep, or as long as many of the other topics that I've been talking about. I expect to make a lot of errors here, and I don't try to hide my errors. If I make mistakes, please tell me. You're encouraged and invited to tell me when I'm making mistakes, because I learn that way as well. In this presentation, I have a couple of handouts. There's this one for my students to use as they interact with this, and this is another one that they will be using to interact with this. It has two sides, so this is the other side. I'm going to have them plot out some of the transistors and what kind of gates they represent. So to start this video, I like to start with what some random website has said, that these are the world's 10 best inventions. And there's a lot of good ones there. I'm thinking there are some that are missing, like the wheel, but maybe that's the thing in the center. I don't know. But if you think about this, all of these inventions, except for maybe the steam engine and the airplane, but in a way, the rest of them we're carrying around in our cell phones, our smartphones these days. But these are the world's 10 best inventions and the years that they were introduced to us. And if you think about it, they're all of them are integrated, again, except for the airplanes and the steam engines, into our phones that we carry around with us. But all of these have pretty much these days integrated what I think is the world's very best, very most important invention, and that is the invention of the transistor. The transistor is really nothing more than a switch. Okay, if this is a blade switch and a schematic of a blade switch, and it's showing that the flow is blocked because the switch is not connected. And to connect the switch, that allows flow of electrons from one side to the other, but it's also allowing flow of voltage, and that's really what the focus is of what transistors do. Open again, blocked flow. And these are great switches, but you can't really make computers out of these because we need the computer to control its own switches. So we need switches that can be controlled electronically by the computer as it completes its list of tasks. The list of tasks, another name for that, is the software program, the application, the code, right? So it kind of runs itself. Well, there are switches that can be controlled by a computer. This first switch is going to be a relay, and it is actually been around quite a while. And it can be controlled electronically, and so let's talk about it. It has a magnet coil, it has a lever on it, it has a hinge, a spring, and some contacts. And of course, the lever, the hinge, and the spring can allow, and the magnet can cause the other set of contacts to be contacted. It's closed when they're in contact with each other, and closed means that electrons are flowing. And it's open when they're not touching each other, electrons are not flowing. So when you put electrons with a voltage into pin A, they will follow this path and come out at pin E, or connection point E. But if you energize the coil, copper windings around a steel pin or peg in the middle, electrons all have magnetism in them, and when you wind them in a coil, it strengthens the magnetism. That magnetism can flow outside of the wire and can be concentrated in the center core, that steel core in there. When that is magnetized, it'll attract the lever, and it'll change the direction of the flow of electricity. So we can use electricity to change the flow of electricity using a relay switch. Turn the magnet off, the spring takes over and pulls it back up and closes the other path, and the electrons and the voltage follows that path. Turn the magnet back on, change the path. That's how it works. But how is a transistor better than a relay? Because this is a relay. We haven't really talked about transistors yet, but they are both switches. And even before the mechanical switch, the relay, there were other mechanical switches that were not electrified, and that kind of takes us back a little further back into the history of computers. In 1642, between 1642 and 1643, a guy named Blaise Pascal invented this computer. It was purely a mechanical, non-electric computer, and he made it to help his father, who was a tax collector. This is called the Pascaline, and it was the first calculator, first adding machine to be produced in quantity and used. It has 8 movable dials and can perform addition, subtraction, multiplication, and division. This is a picture of Blaise Pascal. Another computer that came along a little bit later in 1822 was another computer that used mechanical, non-electric switches. This, I guess about 180 years after the Pascal machine. This is the Babbage machine, also known as an analytical engine. It was also completely mechanical, not electronic at all. And the analytical engine had a new, unique property in that it could be programmed. It was programmable, so you could actually put a program into it, and it would do different things for you based on the program. This is a picture of Charles Babbage, the inventor of this machine, but there's something else that's unique in history about this. This is his assistant, Ada Lovelace. She was the first computer programmer. She was also the first female computer programmer. It's also interesting to note that the first computer programmer was a female. So then electronic computers were built and used. They were built and used before the transistor was invented. I want to talk about some of those. But what did they use for a data switch? Now we're into electronic data switches. What did they use for a data switch way back then? Well, in 1904, John Ambrose Fleming was considering the idea, and he invented something and patented it in 1904 called the thermonic valve, the first vacuum tube. With this advance, the age of modern wireless electronics is born, the first vacuum tube. These are some of the earliest vacuum tubes that were made, and of course they make newer versions of vacuum tubes. One of the first computers to use vacuum tubes was the Colossus. Maybe you've heard of the Colossus in 1943 during the war. This is a picture of the Colossus, and this is a picture of Alan Turing, who developed and essentially invented this Colossus because in Britain in 1943 they were at war against Nazi Germany, who was trying to eliminate them as a country, and what we needed to do was crack their secret code. It was easy to hear the secret code because it went over the radio waves. You could collect it, but nobody could crack it. Nobody could figure out what it said until, first of all, we had to capture our own one of these Enigma machines, these code generators and readers. Somebody on land could have one. Somebody in the submarine could have one. They would use these they would punch the regular message into it, and it would code that into something different. We have somebody here in this location that actually has come to my class and talked to my students. He's built one of these from scratch. It's amazing, and he demonstrates that to my students from time to time. Anyway, this Enigma machine was thought of as undecipherable until we found some of the special instruction books, I guess we'd call them, and we got our own copy of the machine without the Germans knowing, and then we were able, Alan Turing there, he was able to crack that code and use the Colossus, and we knew what the Germans' plans were for several months before the war ended, and very frustrating for them. But that was a nice solution for one of the earliest computers that used vacuum tubes. I don't think I mentioned it. That computer actually used 1,600 different vacuum tubes, and this is a picture of the Colossus and a bank of the vacuum tubes that it was using. So, yeah, there they are, 1,600 vacuum tubes. A couple years later, in 1945, in the United States, This computer was developed. This is called the ENIAC. That is an abbreviation of Electronic Numerical Integrator and Computer, the ENIAC. And it was a first because it was the first programmable electronic general purpose, which means you could program it to do several different kinds of things, digital computer, completed in 1945. And it was large. And here's some of the stats on it. It used 18,000 vacuum tubes. That's a big number, considering that one of the vacuum tubes would blow out on the average about every 20 minutes, according to the story. So they'd have to shut down, find the burned out vacuum tube, replace it, and they were back online after that. But it also used 7,200 crystal diodes, 1,500 relays. You know, that relay that we were looking at a few slides ago. Used 1,500 of those. Used 70,000 resistors, 10,000 capacitors, and 5 million hand-soldered connections. So that is the ENIAC. Vacuum tubes were a problem, and we needed to come up with something else. And theoretical physicists had considered the problem and knew there was a solution. And it wasn't until a couple of years after this, in 1947, that the first transistor was made. And this is allegedly an image of the first transistor. And it was built, or designed and built, by John Bardeen, William Shockley, and Walter H. Brattain of Bell Labs in 1947. Its size may be 4 inches by 4 inches. It is huge compared to how small they can be made today. They are made using photographic and electronic processes. In fact, they're so small today that people don't make transistors much anymore. It's pretty much computers that make computers and computers that make transistors. Here are the three developers, the three designers of the first transistor on the Electronics magazine cover in 1948. Around there, they also got the Nobel Prize for such an amazing invention. And of course, I think it is probably the most amazing invention ever made. Just about everything depends on it. Here is a comparison of actually kind of a small vacuum tube, and then in the middle there is a transistor, and then on the left is an integrated circuit that contains many transistors. The transistors are getting very small. In fact, next thing I'm going to do is show you a quick video clip of zooming into a microchip. Okay, here is an integrated circuit, and on the integrated circuit is, a whole bunch of transistors. And we're just zooming in. This was a longer video clip, but I've trimmed it down and to make it shorter. Now we're down to 60 microns and still zooming in, and we still haven't seen the transistors yet. Zooming in and zooming in, getting closer and closer, getting down. Now we're at 6 microns, zooming in and getting even closer, and there it is right there, the transistor. It's going to show up a little more clearly, down to 1 micron, 1,000 nanometers, and there it is. Okay, there it is. This little square represents a transistor. Each one of the little squares on here represents a single transistor. So they are very small these days. In fact, we're going to talk even more about how small they are. This is a transistor that is used in computers, and it is also identifying its parts. It has a source, a drain, and a gate, and we're going to be talking about those. Now, how many transistors can you fit on a chip? Well, here is one of the more recent record holders. This is the state of the art. This is called a graph core. And the Graph Cores company, it's an AI chip maker from the UK, and it just unveiled in 2020 its new computer chip that packs an amazing 60 billion transistors. That is a lot of transistors. That's about a 2x2 package there. But in looking around in the last week or so, I came across another one that is more dense than that one, and that is this one, the Cerebrus WSE-2, and it has 2.6 trillion transistors. So it has a lot of transistors on it, and our transistors are getting smaller and smaller, and the smaller they get, well, the more they leak, but the more processing power we have as well. Okay, so we're going to be talking about some transistor types, the transistor types that are out there, as well as the ones that we will specifically be using. So this is the worksheet that we're going to be working on. You write in the names as we talk about the different transistor types in there. Again, I am just newly learning about this, so if I say something wrong or make a mistake, please tell me in the notes. The transistor types, though, that we're going to be talking about are starting with bipolar junction. Write this down on your notes. And bipolar junction has two types, NPN and PNP. Now, that doesn't mean anything but negative, positive, negative. See, what they do to make a transistor is they take some sand and they purify it. And that purified sand is also known as silicon. The valence shell of the electron, if it's made up of exactly 4 electrons, it can be either nudged into being an insulator or a conductor. So we mix in impurities with the silicon that make it either more negative or more positive. And then we make a sandwich out of that. So NPN means negative, positive, negative sandwich. So that's like having bread on the outside and peanut butter on the inside. And then there's the PNP, which is the positive, negative, positive version. And sometimes we call these N types, and sometimes we call them P types. The PNP is a little bit like having a sandwich where you take a single slice of bread and put peanut butter on each side. So these are bipolar junctions. This is probably the earliest transistor that was developed. The bipolar junction transistors look like this, and that's all I want to say about them, because I want to get onto the field effect versions. And there are a couple of different types of field effect versions. There's the junction field effect transistor. And I believe, if I'm not wrong about this, please correct me if I am, junction is a type of transistor that continues to either inject or evacuate electrons to and from the gate, and they travel into the bridge that connects the drain and the source to the drain and allows the flow of electrons and, more importantly, the passage of voltage from one side to the other. Junctions also come in something called depletion mode. Depletion mode also, though, comes in N-type, which is, if I understand correctly, NPN, or P-type, which is PNP, and they look a little bit different than the bipolar junctions. This is the junction, and really, as far as I can tell, the big difference is their legs are bent funny. But that's not the kind that we're going to be using anyway, and so let's get on to the kind we're going to be using. We're going to be using some called metal oxide semiconductor field effect transistor types. And those actually come in 2 flavors, the depletion mode flavor, which best definition I can say is these are controlled by zeros, whereas the enhancement modes are controlled by ones. But then we have also N-type and P-type. So the real ones that we're going to be using and discussing are going to be the ones that look like this and this group here. So let's focus on those types, and let's go through and define these as best as I can, these kinds of transistor types that we're really going to be focusing on. First of all, transistor types. Well, a transistor is really just an electronic switch that can be controlled by a computer, by a controller. And So we're going to keep that as part of the name of this transistor. Field effect, as far as I can tell, it uses magnetism to cause flow between the source and the drain. And so that's what field effect means. I think it's a little more technical, but for the level that we're starting out at, that's probably okay. Metal oxide semiconductor, that is silicon. Silicon is the metal oxide that these semiconductors are made out of. So that's semiconductor. We're going to use that in the name of our new transistors that we're going to be using. Semiconductor can either be nudged to either conduct or insulate. Okay, so that's why we're using the metal oxide semiconductor in the name of our transistor. Again, the enhancement mode, not completely clear on that, but I think it means the gate is not, in this case, I think maybe it's more like the field effect, but I'm assuming this means that the gate is not connected to the source drain path. So it's enhanced. I've been getting differing definitions on what enhancement mode means. I'm still trying to figure it out. So active high means it's controlled by ones, and that's the N type, and active low means it's controlled by zeros, and that is the P type. And so we're going to be talking first about the N type. But if you are a designer of transistors and you're making some kind of a controller out of transistors, and you're connecting all of these transistors together, and your assistant Larry is handing you transistors, every time you need a new one, you have to say, "Hey, Larry, please hand me another metal oxide semiconductor field effect transistor, N-type, please. Oh, and the enhanced one." And you're saying that millions and millions of times if you're designing a new bank of transistors. Well, that won't do. So we need to have a shortened name. So we shorten this name to N-type MOSFET enhanced, which really means N-type metal oxide semiconductor field effect transistor enhanced. Actually, we reduce the name down even more, and we would actually just call this an NMOS. So to see how these things work in another way, from another perspective, I'm going to use what's called a water analogy. I've got a copper pipe with some water flowing through it. So this image represents a conductor. Now, a conductor is a broad word. A conductor, they carry resources. So it could be a wire that carries electrons, could be a pipe that carries water, could be a glass fiber that carries light. The analogies on all of these are very similar, but this happens to be a conductor that we're going to imagine carries water. So we want to see what's going on the inside. If this happens to be a pressurized fluid pipe, we're going to say that it is pressurized with 5 volts of pressure. That means it has some kind of a fluid flowing through it. The fluid is being conducted. The pressure is being conducted from one place to another. And then it's a binary 1. So pressurized generally means 5 volts in our world, and not always, but generally. And that is what we call a binary 1 if it's pressurized. If it's drained, then it is 0 volts, and that's what we're calling a binary 0. Well, this is just a conductor. It's not yet a transistor. We need to be able to control the flow somehow. So to control the flow, we're going to add a second conductor. And because this is kind of a physical water-based analogy, the second conductor will control the flow of the first conductor. It's going to be a switch, and I imagine that the switch looks something like this on the inside. Okay, so here is the switch. It's got this valve that will either allow or stop the flow of the fluid, the water. And so here's the water. Now what I'm going to do is add some pressure gauges. Now pressure gauges are going to be voltage gauges in this case, and this one happens to be 5 volts because it's pressurized. When we say 5 volts, 0 volts, well, 0 volts equals a binary 0 and 5 volts equals a binary 1. So on this side of the pipe is a binary 1. On this side, adding the pressure gauge, there is no pressure here, so it is still at 0 volts pressure. We're going to add a third pressure gauge, and this is where we're going to add pressure to the gate, And by adding pressure to the gate, we'll either encourage flow or resist flow of specifically voltage or pressure through the pipe. So I'm adding pressure to the switch, and that raises it to 5 volts. So that's a binary 1 in the switch. That moves the gate in the switch so that it allows the horizontal flow through to the other side of the pipe, which is why the pressure gauge increased to 5 volts, because now we're calling that a binary 1. So that is kind of the water type analogy of how a transistor works, but I want to go the other way with it. We're going to drop the pressure to the switch. That will change the position of the gate. That will stop the flow of water. Therefore, it's a binary 0 in the gate and a binary 0 on the output or the drain of this pipe. So kind of gives you an idea. That stops the flow. And these are red words. I have my students write down the red words usually. I'm defining a transistor at this point. Transistor is an electrical switch that can stop or start the flow of voltage. So if you need to, you can stop or pause the video and write that down and get it into your logbook. MOSFETs, they have, or NMOSs, N-type MOSFETs, they have a drain. And we're representing it like this. This is the schematic symbol of a drain. And then they have a source, and this is the schematic symbol of a source on an NMOS. The drain, of course, is normally 0 volts, and the source is normally 5 volts. And 0 volts is a binary 0, and 5 volts is a binary 1. Also in this schematic is the gate, and we represent the gate in an NMOS like this. And its normal position is 0 volts, and that means that 0 volts of pressure is fed into that, and that of course blocks the flow when it's 0 volts between the source and the drain, and the flow is the flow of voltage. How does that work? Well, to enable the flow of voltage from the source, we're going to set the voltage at the gate to 5 volts, which is a binary 1, and that will pressurize the gate itself, and a magnetic field is then created. The electrons do not jump between the gate and the source drain path. What does jump is something that always accompanies electrons, and that is electromagnetism. So it's magnetism. And magnetism crosses over to the bridge of the source drain path and encourages a flow of voltage from the source to the drain. So the voltage then flows from the source to the drain, changing the voltage of the drain to 5 volts, which is the same thing as a binary 1. So this is a switch where we can switch data from binary 0 to binary 1, and that's kind of how it works. This is what an NMOS or an N-channel MOSFET looks like. It is specifically the IRF540N. This is its gate, this is its drain, and this is its source. Of course, the gate, putting a 1 in there will cause a flow between source to drain. Putting a 0 into the gate will inhibit a source or stop the flow between the source and the drain of voltage. The N channel, normally it's off, but if you put a 1 in the gate, that's 5 volts, that causes voltage to flow. If you put a 0 in the gate, that's 0 volts, that causes voltage to be blocked. There's also one called the P-channel MOSFET we'll talk about as well. The number on this is only slightly different. It's the IRF9 540N. It also has a gate, a drain, and a source in the same locations. Notice it's gate, drain, source from left to right, gate, drain, source. That's important. If you're going to use one of these, remember, gate's on the left, drain's in the middle, source is on the right. Normally this is on because it is a PMOS or a P-channel MOSFET, and that means the gate equals 1. That's 5 volts. That means voltage is blocked with a 1, and 0 causes the flow of voltage from the source to the drain through the source drain path. let's talk about the NMOS a little more. This is what I'm doing here is just showing you a blade switch again, and just showing you that's really kind of how it works. That's how we envision that it works. But because it's connected to the ground, its voltage then is 0 volts, which is a digital 0. The source up there with 5 volts is a digital 1, and the gate is not allowing a flow. We call this an open gate. It's not allowing the flow because it has been pressurized to 0 volts. Okay. If we put a 1 in place, if we put a 1 in the gate, that encourages, that closes the gate and encourages flow from source to drain, changing the drain from 0 volts to 5 volts, or in other words, making it a digital 1. Change it back to 0, that opens the gate again, inhibits the flow, and changes it back to 0 volts or a digital 0. On the other side is the PMOS, and it does exactly the opposite. It's got a gate, drain, source all in the same positions. It's got the 5 volts digital 1 and 0 volts digital 0, and its gate is normally closed. Normally allows the flow to pass from the source to the drain. 0 does opposite thing. In NMOS, it breaks the flow. In PMOS, it causes the flow or enables the flow. Okay, so we just need to remember that these are opposites, and putting a 0 into each of these does the opposite thing. Okay, changes ultimately 5 volts, a digital 1 on the output. If we change everything to a 1, again, it does the opposite thing on both sides, and that's kind of what you need to remember. So now I'm putting these aside and putting in the schematic symbols again for our gates, and just showing you that a 1 will allow flow in the NMOS version, and on the other side in the PMOS version of the schematic symbol, a 1 in the gate will stop the flow, a 0 in the gate will enable the flow. So it's a little bit like what we've talked about earlier, an active low. If you remember, an active low means controlled by zeros, which this is, except that back in active low, when we talked about that, sometimes the digit that caused things to happen, the opposite digit did nothing. And that's where this kind of breaks from active high and active low. In this case, the opposite digit does something. It either enables or prevents the flow of voltage from source to drain. So that's what we're showing. And this connection was released, so there's no change. But if I change everything to 0, it's going to stop the flow in the NMOS, and it's going to enable the flow in a PMOS. So that is, again, the difference. Now, what we're going to do is we're going to use an NMOS to start making gates. At this point, because we're going to be making gates, it's time to get out this worksheet. And as always, once you understand what's going on here, I encourage you to work ahead of me and see if you can get the answers to identifying these various gates before I actually give you the answers. That way, if you get stuck, you have a question in your mind, and when I get to it, you get an answer. So anyway, here we are. We're going to make a gate. I'm going to make a NOT gate, an inverter. So to make an inverter, I'm going to need a power source. So I'm just going to put a VCC 5 volts in the top, and that of course is a digital 1. In the drain down below, we're going to just connect a ground to it. That is 0 volts or a digital 0. The gate is also where you put in the logic input. With a NOT gate, we had 1 in and 1 out, and so this is where we will put the 0 in, and that depressurizes. This is an NMOS, so that blocks the flow, and that means none shall pass if we put a 0 into the gate. This purple line represents a conductor where the result of the NOT gate inverter comes out. So this is the logic output. And we want our NOT gate, if we put a 0 in on the left, we want a 1 on out of the right. And so that is, in theory, what we'd like to see. But what really happens is not quite that. I'm going to open the gate and put a 1 in. The 1 enables the flow in the bridge between the source and the drain. And that allows the voltage to pass, right? And so the drain becomes a binary 1. But there's two problems with this type of a gate. The first problem is that we're connecting power directly to the ground. That is a problem. In fact, that's always a problem. The problem is if you connect power directly to ground, it's going to heat up and maybe cause a fire, but it's going to destroy the transistor. And so that is the first problem. The second problem, if you notice, is that we put a 1 in and got a 1 out. So output didn't really change, right? So we're going to try it again, only this time we're going to slow the flow. That will keep the... See, what happens is when you connect power directly to ground, there is no resistance, which means the electrons can flow as fast as they want, faster and faster, and what they do is they collide with the different atoms on the inside. They release a lot of heat. That heat builds up, and there's no control of the heat, so eventually it ignites things or melts things or destroys things or whatever heat does to things. So the solution to that is to slow down the flow. And we're going to do that by putting in what's called a pull-up resistor. That pull-up resistor is right there, and the reason we call it a pull-up resistor is because the pressure is a pull pressure. We sometimes think of the pressure on a circuit as a push pressure, but that pressure is a pull pressure, like putting a vacuum cleaner onto this gate, onto this circuit. And what that's going to do is when the gate is not allowing flow, then the output, which is connected to the high or the 1 or the 5 volts, will be a high, a 1, or a 5 volts until we open the gate. We put a 1 in, the 1 allows flow in the gate, and that pulls up the drain to the level of the logic output, changing it to a 0. So we have two solutions. First, the power is not connected directly to ground, and that prevents fires. But the second thing is that the output actually did change to the opposite of the input. So what happens when we put a 0 into the input of this gate? Well, we put a 0 in. That prevents flow across the bridge connecting the source and the drain, and that means the source above becomes 5 volts again, and that means we put a logic 0 in and a logic 1 came out, and that is exactly what we want our NOT gate inverter to do. So this actually works. All right, going back to the earlier slide, we're asking the question now, can we do the same thing with a PMOS? Can we make a NOT gate from a PMOS? Now, what we just explained about a PMOS or about the NMOS was actually answer A on your worksheet. And so if you can remember how that all worked, you might want to fill in that truth table and demonstrate why that is a NOT gate. Pause the video if you need to. Okay, so can a PMOS be used to make an inverter? Well, let's try. Let's hook it up like we did before. We need a source on this thing. That's the 5 volts, the VCC, the digital 1. And that is known as high pressure, digital 1, all the way to the bridge of the source drain path. We've got an output conductor here. That will be the logic output. We hope for that. Well, we know right now that that's a 1 because its voltage, its pressure, its only pressure source is the VCC 5 volts. Even though it's going through a resistor, it's still the high pressure. We have the pull-up resistor there. Down at the bottom, we're putting the drain, the ground. We're plugging it into a ground. That's 0 volts. That 0 volts can flow up right to the point where the path is stopped. In the gate, that's the logic input. If we put a 0 in there, that will block the path. So that's really currently what's going on. And the two are not connected. Remember, 0 allows voltage flow, and a 1 blocks the voltage flow in a PMOS. Remember, that's the opposite of an NMOS, where a 0 blocks the flow. In this case, a 0 allows the flow, and a 1 blocks the flow. So 0, we're just allowing the flow, and the flow was pulled up from the ground to the logic output, and it became a 0. Hopefully you see the problem. We put a 0 in, and we got a 0 out, and that is not a NOT gate inverter. So what we have to do with a PMOS is use a pull-down resistor instead of a pull-up resistor. What that means is we're really just moving the resistor's location down towards the drain, and then we're calling it a pull-down resistor. And we also have to change where the output is placed. So repositioning the output to the lower side as well. So now the higher voltage will flow down if the gate is open, and the output will be a 1 if the gate is opened, but whenever the gate is closed, it will be a, well, it's the opposite. When the gate is allowing flow, we should get a logic output of 1. When the gate is blocking flow, we should get an output of 0. And of course, that means that we're really pulling. This is also another pull pressure on here. And so here is the pressure flowing through, and because it gets to the output with the high pressure, the result is a 1. Okay. 0 in. We got a 0 in, we got a 1 out from this, right? So this is an inverter. So we can. Okay, let's talk about another gate. This is going to be on your worksheet. It's going to be area B that we'll be working on. Try to work ahead of me on this, but if you're not quite ready to do that, do your best to understand. We're going to be making an NMOS gate. I've got the VCC to start out with. Zigzag line, like on Charlie Brown's shirt, that is a resistor. That is a pull-up resistor because it is up high on the NMOS rather than down low on the PMOS. That is another transistor symbol. That is an NMOS transistor symbol. That will be input A. We got another NMOS transistor. That's going to be input B. And of course, it's capped off on the bottom with a low voltage source. We're calling it a ground. And then the output of this, just like before on the NMOS, is up above by the resistor. That is the output F. Next thing we want to do is maybe run some pressure through this. Pressure from VCC is flowing down, so the output, when the gates are in their normal position, the output will be a 1. And the ground on the bottom is a source of low voltage, and it's blocked because we haven't identified the gates as open or closed. Now I've just put a truth table on the screen because the truth table is the way beginners identify what gate they're looking at. But let me give you a quick preview of that. You can see 2 NMOSs in series. That means for any change to be made, both NMOS transistors have to be allowing flow. Input A must be allowing flow, and input B must be allowing flow. When you see these transistors in series, then you realize that what you have is something from the AND family. It could be an AND or it could be a NAND. But if they're in series and something has to go through one and the other, what you have is a variety, don't know yet which kind, but a variety of an AND gate. Going to populate the truth table. Remember, the inputs are always just a binary count, and I have an index row on here as well. And then the outputs will be F, and that's what we're trying to figure out. So with row 0, with row 0, we're going to be putting an A in for the first gate, gate input A, and a 0 in for input B, to both zeros. What do zeros do with NMOSs? Well, they prevent flow. If the zeros are preventing flow in the transistors, that means the only output that could possibly be coming out of output F is high voltage 1, binary 1. What if we open one of the gates? We're going to allow flow through gate B because we are feeding it a 1, but we're blocking gate A with a 0, which means technically the ground level of voltage will not reach output F either, because both gates have to be allowing flow. Okay, so output is still F. What do we reverse that? If we allow flow through the other gate, that would be A, but block voltage in B, still, even though A is open and the high voltage can get down a little ways, still gate B, input B, is blocking the flow, so the output is still F. Okay, so the last possible alternative is that we're going to open both of the gates by putting 1s into them. If we put 1s into both gates, that will allow flow from the voltage of the flow of the low voltage upward up to the output F. Now, originally it looks like the voltage is falling, but that is overcome by the low voltage because it's being pulled up. So the output in this case has to be a 0. So if you understood that, you might be able to work ahead on the next gate. And but before you go, we should probably identify which gate this is. Well, we have an output of 1, 1, 1, and 0. Now, my students should know by now, they should be familiar with this pattern of the truth table, and they should realize that this is a NAND gate. This is a NAND gate. Basically, what we're doing is multiplying A and B and then reversing the result. So A times B is 0, reverse the volt and reverse the result, and there's a 1. 0 times 1 is also a 0, reverse the result, and you've still got a 1. And 1 times 0 is a 0, reverse the result, and you still have a 1. 1 times 1 is 1, reverse the result, and you get 0. This is a NAND gate. Okay, so there it is, the NAND gate. Now, we're on to gate C, which is including a NAND gate. What we're doing is we're setting up a NOT gate on the outside of the NAND gate. So if you can see that, all we're doing is inverting over on the schematic symbol of the NAND gate. You've got a bubble on the outside of that gate. That bubble, if we can cancel that bubble out with a NOT gate, then it will be an AND gate. One thing that you should realize from this is that the NAND gates require 2 transistors, where a AND gate requires 3 transistors. Okay, so we're putting a NOT gate on the outside of the NAND gate, and then we're combining them, and that actually inverts all of the outputs for the NAND gate, and now the truth table is an AND gate truth table. Combining the 2 gates eliminates the bubbles, as we learned when we talked about bubble pushing. And so this configuration of transistors, NMOS transistors, are pull-ups. This configuration is an AND gate. Let's try another gate. This gate, this time, notice the difference in configuration. These are still NAND transistors. A and B are still NAND transistors, but they are configured in parallel. That means the pressure has a choice of which direction to go, which gate to go through. So it could go through transistor A, or, I focused on or there, or it could go through transistor B, or it could go through both. Okay, so we know that this is going to be a member of the OR family, whether it is an OR, a NOR, an XOR, or an XNOR, but it is a member of the OR family because you can see that by the pattern of the configuration. Plugging ground into it, letting it flow as far as it wants, but the gates are undefined as whether they're open or shut. If we put a 0 in for A and a 0 in for B, there will be no flow between the gates, which means there is no change. F is going to be a 1. If we put a 0 into one gate, A, and a 1 into the other gate, B, well, A will be blocked, but B will allow the flow of electrons, and what that means is the ground will be pulled up and become the result of output F, so that's a 0, because that's ground. 0 volts means binary 0. Okay, next row. This time, we're going to open A and not B. We're going to allow flow in A and not allow flow in transistor B. That's going to be the same result as before because we've just opened one of the two paths and the output ground will go through one of them, and that means F will also be a 0 voltage out. All right, the last possibility is where we just open both gates, and that means that the 0 voltage flows through both pathways out to F, and that means that that is also a low. And if you look at that truth table, you say, okay, where have I seen this before? We know it's one of the ORs. If you add A and B, 0 plus 0, that's a 0. Flip the result, you get a 1. 0 plus 1 is 1. Flip the result, you get a 0. 1 plus 0, well, that's a 1. Flip the result, you get a 0. And 1 plus 1, or as we like to say, true plus true is true. Flip the result, and you get a 0. This is a NOR gate. This is a NOR gate. Looks like this. And, of course, we've got to convert the NOR gate to a NOT gate, so I'm installing a NMOS pull-up NOT gate on this, which will reverse the outcome on the truth table. And so we're just reversing the outcomes on the truth table really quickly because we're knotting them as they come out. Double knots kill each other, and so now we've got a regular OR gate. Taking a NOR transistor, or taking a NOR chip, a NOR gate, I guess that's the best way to say it. A NOR gate only has 2 transistors. It takes 3 transistors for it to become a regular OR gate. Okay, what else we got here? Well, we've already put together an AND gate, that is a NAND with a NOT. The OR gate, which is a NOR with a NOT, and the NOT gate, which is just a NOT. We have developed all of the gates we've been using all year, A and O or, and I or NOT inverter. These are all the gates. We've just shown you how to make all of the gates. But that's not the end of the story. We also know how to make NAND gates. Those are the universal gates that save, they save weight and cost and everything else. They make circuits more efficient. And of course, if you knock the NOT gates off all of these, you have the universal gates, the NAND on the left and the NOR in the middle. So we've actually constructed all of the gates. But there's more. NMOS and PMOS gates require the use of continuous voltage. But there's another alternative called CMOS. And what does CMOS mean? Probably should write it down. CMOS is the combined use of NMOS and PMOS transistors. What that does is it eliminates the need for resistors, so those can go away. So I've got an NMOS here. I'm putting the resistor back on it. The reason I'm putting it back over here on the right is because I want to compare it as I build its CMOS counterpart, which is just, CMOS means complementary metal oxide semiconductor. That's what CMOS stands for. And so we're going to use a truth table, and we're going to build a NOT gate. So we're going to use an NMOS, and we're also going to be using a PMOS. Okay, that means it's complementary because it's using both kinds. Next, we're putting a VCC power supply on one end of it, and a ground at 0 voltage on the other end of it. And our input will be through A, so that will be input A, and that is connected to both the PMOS and the NMOS. Coming out of this thing, we have F, and it's connected to both as well. So looking at this, that's the output, F. What we're going to do then is put a 0 into this and see what happens. So if you put a 0 into this CMOS, well, that flows both to the PMOS and the NMOS. So if you're flowing both directions, what does a 0 do with a PMOS? Well, it allows flow. What does a 0 do with an NMOS? Well, it prevents flow. So remember, the NMOS uses 0 to block passage of voltage, and the PMOS uses 0 to allow the passage of voltage. And so you could just see the voltage began to pass because the 0 went into the PMOS, and now it's flowing. But it's blocked by the NMOS, and the benefit of having one of these gates always blocked is that you never connect power directly to ground, so we don't get fires. Okay. The output then is, notice the 0 opened or allowed the flow through the PMOS gate, and that allowed the flow to come down through F. So really, F is going to be a 1, which means high voltage coming out. But if we switch it, if we switch the input to a 1 and allow that to flow, what does that do? Well, NMOS uses a 1 to allow passage of voltage, while a 1 in PMOS uses 1 to block passage of the voltage. And so one of these gates will open and one will not, so power will never meet ground. And it looks like 1 is blocking passage through the PMOS, which means ground and its voltage, its 0 voltage, is going to go through and change the output to a 0. So this is a gate that actually uses both PMOS and CMOS, and it's a NOT gate. I'm building another gate here. That's what's going on here. This is a test-like question that I like to give my students. I say check all the boxes that apply. This is an NMOS or it's a CMOS. It is an AND, a NOR, an inverter, an AND, an OR, an XOR, or an XNOR. And so your job as a student is to figure out, what is this beast? So I'm just hooking it up. There it is. That is it. And hooking it up to the ground. And really, to identify it, the best way to do it for new people just into this, is to use a truth table to identify it. So there's our truth table. Remember, it's just a binary count on the inputs, and there's index numbers for each row. And so we're going to put a 0 in for A and a 0 in for B. So what I've done is release the voltage. Now it's flooding as far as it can. It's blocked by the PMOS gates. Going to do the same thing with ground, and now it goes as far as it can before it's blocked by the NMOS gates. And now I'm putting a 0 in to input A. That is flowing in two directions. It flows up to the PMOS, and what that means is 0 in the PMOS means that the PMOS is going to allow flow. Down on the other NMOS gate, a 0 blocks the flow. So you can see that the flow has gone from the VCC out through F. This is, you put a 1 into this, you put a 0 into this mystery gate, and you get a 1 out of it. Okay, but we've still got the other 1 to do. How can I be so sure that the answer is 0? Well, putting it in, I got that out of sequence. A 0 will allow flow through the PMOS gate, and it will block flow through the CMOS gate. Well, the high voltage has already gotten through on the left side to F, but it's going to get through as well if it wants to through the right side to F, and that's why I'm so sure that that is a 1. Let's try the next row. And this row, in row 1, we've got a 0 going into A, and that, of course, flows upward toward the PMOS and horizontally toward the NMOS. A 0, of course, is going to allow flow through the PMOS. Notice, I don't know if I mentioned it enough or as strongly as I should, but PMOSs always have that bubble on them. Okay, so just make sure you realize that that's how I am instantly able to see which one is a CMOS and which one is a PMOS and which one is an NMOS within this greater CMOS. Okay, so a 0 in the PMOS zero in the PMOS allows flow in the PMOS and blocks the flow in the NMOS. So now the voltage can flow down toward F through that open gate or that allowing gate, and that means we have a 1 on the output. Well, I haven't even put a value in for B yet. How do I know that's going to be a 1 output? Well, there's the 1 going into the B, and that blocks the PMOS, but it enables the NMOS. Well, if the NMOS is enabled, that low voltage is going to flow through, but it's just blocked by the other gate. So the output is still a 1. So now the next row, row 2. We're going to put a 1 in for A and a 0 in for B. It's just going to do the same thing. It's just going to be the opposite gates or the other gate. So let's do it. 1 in for A. What that does is it makes a high voltage, 5 volts, flow toward the PMOS and toward the NMOS. Well, a 1 blocks the flow through a PMOS, but a 1 allows flow through the NMOS, but there's nothing to flow through the NMOS because down at the ground is stuck behind that other gate. The low voltage is stuck behind that other gate. So right now, F is undetermined. But if we put a 0 in for B, well, that's going to flow horizontally and then vertically up to the PMOS. And that means a 0 is going to allow flow through the PMOS, and the 0 is going to block flow through the NMOS. So the ground isn't going anywhere, but the high voltage 1 will be able to flood the system and come out through F. And so we have a 1 on the F output. All right, this last one, we've got 2 1s going in here, 1 for A and 1 for B. Putting the 1 in through A, it flows horizontally to the NMOS, flows vertically to the PMOS. A 1 on a PMOS blocks the PMOS. A 1 on the NMOS allows flow, but there's nothing to flow through. So let's put the 1 into the input B. 1 into input B, that flows horizontally to the NMOS and flows vertically to the PMOS. And the PMOS, 1 in a PMOS, that stops flow. But a 1 in the NMOS allows flow. And now, in this instance, both gates are allowing flow. For the ground to flow through, that means that the ground or 0 voltage or a digital 0 flows out through F. So we can put that on our truth table. What have we got here? Let's think about it for a second. On the truth table, 0 times 0 is 0 flipped over to be a 1. 0 times 1 is 0 flipped over to be a 1. We're multiplying here. 1 times 0 is a 0, flip it over to be a 1. And 1 times 1 is 1, flip it over to be a 0. We have a CMOS version of a NAND gate, and you can compare that to the chart of gates. By now, I'm kind of hoping that you've got it all memorized. Anyway, this is a NAND gate, CMOS style, because it matches what we know about NAND gates, right? So there it is. Well, maybe we don't want a NAND gate. Maybe we want an AND gate. What are we going to do? Well, we're going to take the CMOS version of a NOT gate, an inverter, and we're going to plug it into the output of the NAND gate. That will flip the result and give us a AND gate. NAND with a NOT means AND. NAND combined with a NOT, well, that pops the double bubble, and that gives us an AND gate. So this is a CMOS AND gate. A NAND with an inverter on the outside, in this case, on the right side. Okay. So now we're getting to gates that are a little more complicated. What I'm hoping to do here is to give you, well, I'd like to give you enough time. I'd like you to stop the video and see if you can figure out what kind of a gate this is. But I'm going to keep going. But if you think you can figure it out before I tell you the answer, you should try. Okay? So what have we got here? This is a new gate. We've got a 0 and a 0 going in. We've got power and ground there. We better flood those conductors and allow the power pressure to go as far as it can. Same thing with the ground pressure. Allow it to go as far as it can. And then we're going to be working on row 0, putting a 0 in for A, and that flows over to the PMOS. A 0 into the PMOS allows flow, so the flow can continue that far. Now, the 0A will flow down to the lower NMOS, and it blocks flow. A 0 will block the flow in an NMOS. Doing the same thing with B. B flows in, and it allows the continuance of the flow of the high voltage until it gets to those two gates. Putting a 0 into the B, well, putting a 0 into the B sends a 0 to the NMOS, and that blocks the flow. So still, ground is not getting through those two gates, and neither is power for that matter. So up at the upper PMOS, we've got a 1 going into the PMOS. That blocks it. But down here, we've got a 0 or a 1 going into an NMOS, and that allows flow through that gate. And that flow goes to the outside, which means you put a 0 into this thing, and in both A and B, and you're going to get a 0 out. Let's talk about the next row now. We're going to leave A set at 0, so we really don't need to change much about that, although we will restate that a 0 into a PMOS allows flow, and a 0 into an NMOS blocks the flow, and then a 1 into B, which is the big change here, is going, well, the 1 going into a PMOS blocks the flow, and a 1 going into the NMOS allows the flow, and that means now we've got ground. It's got a path in through everything. And so it can go that far. It can go to the final NMOS and PMOS, affecting those gates. 0 on a PMOS is going to allow flow, which means the high voltage is able to flow out through the gate. Okay, so there we go. Let's go to the next row. What we're really doing is flipping the two inputs. But if you think about that, this whole thing is really quite symmetrical. It should be the same answer, but let's do it. A 1 into the PMOS is going to block the flow. A 1 from A to the PMOS will block the flow. A 1 from A also flows down to the NMOS, and that allows flow. Let's see where that flow goes. It's going to go up into all the wires that it can, all the conductors that it can, and it's going to stop at those other two gates at the end, and we haven't even done anything with B yet. So B, 0 goes into B, 0 into a PMOS, enables flow. It's just going to let the ground flow up a little bit through there. It's the 0 blocks the flow through the NMOS down below. So really there's not much change there. So on the gates on the right side, a 0 blocks flow through an NMOS, but it allows flow through a PMOS, which means we're going to get an output of 1 again. Next one, the last one, row 3. Well, row 3, A already has a 1 in it, but we're going to talk about that again. A with 1, that's going to stop the flow through the PMOS. Going down now to the lower NMOS gate, a 1 allows the flow, which means we can watch the low voltage flooding the internal conductors. They stop over there at the 2 gates at the right, and we haven't done anything with B. Well, on the right, you can see that a 0 blocks the flow in the NMOS, and it allows the flow through the PMOS. It's allowing flow to a high volt, so high voltage gets out. That's a 1. We could put that one on our truth table, but let's finish off B. B, that's a 1 that goes into the PMOS, which of course is blocked by 1s, and a 1 going into the NMOS, which of course allows flow, but that's not very exciting because it was already there. So now we can go over to the right side and look at what is going to happen to those gates. It looks like a 0 going into a PMOS. We know that's going to flow. We already have seen that it's flowed over to the F1. The 0 into the NMOS below there blocks the flow. So we have 1 here. We got 0, 1, 1, 1. If you look at this, anytime there's a 1 on the input, there's a 1 on the output, and that is how we remember what kind of a gate an OR gate is. That was an OR gate there, in case you didn't catch that. That's an OR gate. All right, so let's do this one. This is the last one. Let's figure out what kind of a gate this is. So the new gate, we're going to put, well, VCC is a 1. We're going to let that flood as far as it can. And ground, that's a 0. We're letting that flood as far as it can. And now we're going to be talking about the first row. And in the first row, we have a 0 for A and a 0 for B, like we do. A has a 0. That means that 0 is going to flow to the PMOS and the NMOS. On the PMOS, well, on the NMOS, that's going to block the flow through that gate. On the PMOS, that will allow flow through that gate, so we can actually flood the internal conductors as far as they can go until they meet a gate. But also notice that the A input reaches around over the top and down and stops, trying to flow through the final PMOS on that side, but we don't know if it's going to flow or not, because what is B? Let's check the table. B is a 0, plugging a B into there. That pressurizes at 0 volts the conductors going to PMOS and NMOS. Well, a 0 volts is going to allow flow through a PMOS, and it's going to block flow through an NMOS. That means green, that is low pressure, 0 volts, a binary 0, flows to F, and so we put on the output F for row 0, a 0. What about row 1? Well, A already has a 0, B has a 1. So really all we need to do is change B here. We are now pressurizing the transistors on the right with a 1. Well, a 1 will open an NMOS transistor and allow flow through, but it'll block a PMOS transistor. And so with flow, the flow that actually flows through is a high pressure 5 volts binary 1. So we're going to put that on our truth table in that row. Next row. On this row, we're going to put a 1 for A, and of course that's going to flow to the PMOS and to the NMOS. The PMOS is blocked by 1s, and the NMOS allows flow with a 1, so that means we're flooding the internals of this with a 1, and the 1, or with a 0 from the ground, And then A is a 1, and that flows around to trying to get through the PMOS on the right side. B, on the other hand, is a 0. So what do we do with a 0? Well, a 0 allows the flow of a PMOS, but blocks the flow of an NMOS. That means that 1 is going to flow through. That means that the outcome F is 1, and it also means that on the truth table, the output is a 1. Let's talk about the final row. On the final row, we have A, which is already a 1, and B, that's the only thing we've erased. It's a 1. It flows high voltage to the PMOS, which is going to be blocked, and high voltage to the NMOS, which is going to allow flow through it. That means that we have low voltage flowing through to the output F, meaning that output F is a 0, and on the truth table, the output for row 3 is also a 0. So what is that thing? What is a gate that is a 0, 1, 1, 0 on the output? Do you remember what that gate is? Hopefully you remember that that is a XOR gate. So, we've been through all of this. We've introduced, given you the history of transistors, told you what kind of transistors there are and which ones we use. We actually use pull up and pull down. I believe that's the kind we're using when we use a chip to wire a prototype on a breadboard. Then CMOS, we see those used in computers all the time. CMOSs are a little more reliable, a little faster, but more expensive because we're using 2 transistors instead of 1. We've actually followed through several different gates, following the flow through various transistors and learning how to do those. For my students, there is a test coming up soon, as soon as we can get all the answers given, all the questions answered, for possible questions from this. So hopefully this was a useful video. And again, this was new to me, so if you have insights that I could include on my next iteration of this video, I'd sure appreciate you sharing them with me. Tell me where my mistakes are. I am brave. I can handle it. Thanks for listening. This is Aaron Jerome at Jerome Electronics. Talk to you next time. Bye-bye.